My project is on physics-informed neural network for predicting the ocean wave propagation and elevation. So the application is um, in monitoring how water waves in ocean and sea data near the coastal areas uh, have uh, elevate and propagate at different times. So the presentation outline is basic. We speak about the wave equation, the introduction of the project, the literature review, problem formulation, the methodology, the model architecture, and the model training and results. So overview of the wave equation, it is second order scalar partial differential equation, which can be described the wave equation can be described can describe both water waves, sound waves, electromagnetic waves such as the light waves, mechanical waves as the seismic waves which propagate within the ground. And so we have taken to model water waves. So we have taken the general equation of wave and solved it using the approximation of spatial and temporal values. So we use that equation and translate that um, uh, uh, into the tensors of the spatial and temporal tensors that we feed it into the physics-informed neural network, because the physics-informed neural network is is modeled in such a way that it can understand the underlying properties, the physical properties of the wave. And so we have used synthetic data for training and testing initially, and then use a real world data set from the state of Queensland, Australia, which has 15 coastal areas, and the data set is around, it has 6,000 rows in the CSV file, with the capturing the significant wave height, the latitude and longitude, the positional elements, the time difference, which is the date and time translated into seconds for the time step of the wave. Yeah, the application of our project is in water monitoring applications, where it can be used to monitor the waves near the coastal areas, and help predict any high tides and prevent population from going into the beaches. And it also further research would help it predict tsunami waves, which would help in disaster management prevention. The four main topics of that I have, sorry, the four main papers that I have reviewed are EMRASI, which introduced solving the scalar wave equation using supervised learning, using numerical data, and then feeding it in the physical properties of the wave using real life data set. And then it was able to solve the wave equation and predict the propagation of waves, which was very new at that time. And the main papers that we have used to model our own project is Taco de Wolf and Liu Yu. Taco de Wolf has implemented the physics-informed neural network for ocean modeling, which is the first paper probably in using physics-informed neural network for ocean modeling. And it was able to predict the propagation and elevation of wave between 0 to 0.13 seconds. From the third paper, we understood how to use synthetic data to solve the wave equation, and initially use the synthetic data to solve the finite difference time domain model, a time domain method using the traditional method, and then using that to compare it to the physics informed neural network. So having a comparison or validating the physics-informed neural network from the traditional method. And then the final paper, which was a recent development in, it was able to predict water waves, the propagation and elevation in offshore energy structures where the water waves are used to produce or generate electricity. So it was able to predict the amount of wave propagation and elevation required to produce a certain amount of energy. And that's how we were able to understand how to solve the scalar wave equation and then model that into the physics informed neural network by using by approximating the spatial and temporal time values using a loss function that using a customized loss function that penalizes the discrepancies or deviations the PIN model takes, deviations the PIN model has while solving the wave equation. And the problem formulation is that the traditional methods, they can't exactly compute a large number of real-time real-world data sets because they are limited for scalability, and it is not computationally efficient, while the new deep learning models, the physics-informed neural network, are able to generalize or solve the wave equation and then create a generalized model that can be used to solve water waves, sound waves, light waves, and seismic waves. So we are focusing on water waves to predict the propagation of and elevation of ocean waves using real world data set from the Queensland state of Australia with 15 coastal areas. The physics-informed neural network is it is reliable and accurate because we have tested it against the traditional finite difference time domain method, and we get pretty much accurate accurate results. And it is computationally feasible while using graphical processing units to compute large real world data sets and predict the propagation of ocean waves. So the methodology we have taken is to identify the initial and boundary conditions which of the wave, that is the derelict and Newman conditions, which specifies how the wave reacts when it touches the boundary. And we have created a simulated environment mesh, which is the spatial domain denoted by the x-axis. It is from the origin is 0, while the negative values it ranges from -1 to 1 with 0 as the origin. So negative values is just the coordinate system, and describing the positional factor of the wave. And t-axis is the time step, which is 0 to 0.2 seconds, which is read in the papers previously as the definitive way of modeling one wave is from 0.20 seconds. The boundary conditions, the Dirichlet and Newman boundary conditions specify how the wave dissipates, or the energy is how the energy reacts when it hits the boundary. So initially we've set it to 0, so that because it's a controlled simulated environment, the mesh, and the CFL Cohen-Friedrich-Lewis condition is so that the numerical time step, the time step of the wave, is small enough to match the spatial step size. As we said, the loss function, the customized loss function, penalizes the deviations of the PIN model while during training. And So the methodology also speaks about training the pin model and visualizing the pin model's accuracy and loss results. The code implementation is based on PyTorch libraries, which uses the tensor and autograde for optimizing the gradients using the Atom optimizer and pandas to preprocess the dataset. So this is the pin model architecture, which takes the two-dimensional tensor, the x and the spatial and the temporal values, which is preprocessed by the real-world data set is preprocessed the spatial positions. So the latitude is being preprocessed to longitude is preprocessed to give the spatial position, while the time step of each wave is preprocessed to represent the t-axis, and the target value is the significant wave height, the three hidden layers with 128, 256, and 128 neurons. And it uses the sign activation function, which is useful in modeling the curvature or the wave-like patterns. And so we use the sign activation function. And the final layer is what produces the solution of the wave, which gives us the crest and the trough of the wave. It is a single output neuron. As we can see, the training results, it gives us so this is the real world data set that we have used. We're training it for 1,000 epochs, and the light blue suggests the elevation of the curvature of the wave, the crest, while it goes to dark blue suggests the trough of the wave, and as we can say, the t-axis is the time step of 0 to 0.2 seconds, and the x-axis is the coordinate system, which is from -1 to 1, and the z-axis is the function u, which is the function u is the approximation of the x and t values. As we can see, the real-world data set, this is a subset of the wave, and it is the approximation based on 15 postal areas. And this is a simulated mesh environment that we have created with the losses around 1.5%. And we have compared our pin model to the traditional finite difference time domain by using synthetic data. So we have generated synthetic data to solve the numerical using the numerical equation, the finite difference time domain method, and then compared that to our pin modules result using the same synthetic data. As we can see, the previous slide is the real world data, and this one is the synthetic data. And so we validate the pin model because it is an exact replica of how the traditional methods would produce the solution. And so we can say that our model performs accurately good in generating the propagation and elevation of the wave, ocean wave. And this is the loss curve of the pin model that suggests the loss of synthetic data versus real life data. The real world data loss is quite higher than the synthetic data because there are multiple physical factors affecting the real world, such as the significant height, the positional element as the longitude keeps changing for coastal areas, and the time difference is quite variant for the real world data, while the synthetic data is in a sequential order ranging from 1 to from 0 to from the positional elements range from -1 to 1. So the synthetic data is quite easy for the pin model to understand and train over, while the real world data has the underlying physical properties, and so the loss is around 1.5% or so. And to conclude, we have implemented the physics-informed neural network that that is able to predict the propagation of ocean waves and propagation of and elevation of ocean waves on the real world data set. We were able to do this by understanding the previous works done by Taco de Wolf and Liu and M. Rasi, so that to solve the scalar wave equation by function approximation and using approximating the the spatial derivative and temporal derivative of the partial differential equation, the wave equation, and then formulating that into a tensor by feeding it our real life world data into the spatial and temporal domain as a tensor into the physics informed neural network for training and testing. So our model is able to predict, as I said, the propagation of wave for real life data for the Queensland state for different coasts, and it can potentially help in water monitoring applications. And with further work, it might be able to help in predicting tsunami waves. And our model also able to capture complex physical properties efficiently from large data sets and compute them in a high and efficient and accurate way. Thank you. These are the references with the data set, and these are all the papers that I referred.